All right, well, thanks for joining, everyone. I'm Alex Wood. I'm a software developer with the AWS SDKs and Tools team, and I work on the AWS SDK for Ruby, and a couple other things that will come up over the course of this talk. So why are we here? We're here because our data is valuable for many different reasons, and I've talked to many of you over the course of the conference so far. And as your businesses have been scaling up, as your number of users are scaling up, you have a lot of data, and there's a lot of value in there that you want to get out. Now, this data comes in many shapes, many file formats. It comes in many sizes, from small files that you grep through to petabytes of log data stored across S3 files, and many sources. Sometimes you have those logs in S3, sometimes they're on local instances, sometimes you're needing to copy from databases or from any number of other sources. And in many cases, this starts out as a reactive process. Something went wrong, or our conversions just dropped. We made a bunch less money last month, for example. Why did this happen? We have no idea. You have a bunch of logs and the answer is in there somewhere, and you craft a purpose-built job and figure it out. Or your system goes down. Where was the error that caused the problem? And what you start to find over time is these purpose-built reactive jobs don't scale very well with your time. So how can we get proactive? How can we build the solution before we know exactly what the problem is for as many cases as we can? So a little secret, this talk is not for you. This talk is actually for me about 2 years ago, where I had to face this kind of problem and made a lot of mistakes along the way, or had a lot of difficulties that didn't have to happen. And my hope is that as you go and face these kinds of problems in your own working lives, that this can make it a little bit easier for you, and you can get going a little bit faster than I could. So what are we going to go over? Well, we're going to build today a log processing system. We're going to go all the way from logs in S3 to a Redshift database where you can generate regular reports and have the ability for people to make ad hoc requests. And to get there, we're going to talk about how you can build log processing jobs. We're going to talk about how you can automate it so that your time can scale. We're going to talk about how you can get this information into Amazon Redshift. We're going to talk about how you build reports on top of Amazon Redshift, which, you know, even then my talk is slightly out of date because we've already released a new service to help you do this. But it gives you a good starting point. And finally, we'll get into some of the lessons I've learned as you start to build a system at scale, and maybe go through a few roadblocks that you might encounter as you go through the same thing. So one thing I'll point out is we are going to go into the code level. So we're going to be doing a little bit of live coding and walking through a little bit of code. And all of the code that we're going to go through is available on GitHub right now. And after the session is done, we'll have the links in the slides, and I'll tweet it out afterwards. But you can go through this and play around with this, and this is all you need. Everything you need to do everything we're going to do in this talk is in this repo. So what I'm trying to promise is no black boxes. We're not going to say magic A plus magic B and then it works. We're going to go through every detail that you need. So where are we starting from? This is a weblog that, roughly speaking, is in a standard weblog format. You have IP addresses, user information, user agents made quite a bit smaller to fit in a slide, and information about the kind of requests that they're making. So this is going to be the example data we're going to build on top of. And we're going to go from weblogs like this to output that can be digested by human beings, such as regular reports on what's going on inside the system, or the ability to do ad hoc queries to answer the questions that your product managers, your CIOs might have that you as the builder of the system didn't know they would be asking. So what goes into this system? To start off with, we have logs in Amazon S3. This is not the only input source that you could use, but it's the most common pattern that I've seen. And we're going to start with, if you have these logs, what can we do with them? We're going to talk about processing these logs using Amazon Elastic MapReduce. How can we take these logs and transform them and filter them into something we can use? We're going to, again, ingest them into Amazon Redshift and talk about how we can build reports from that. So let's start by going through how do we write a log processing job. So I have gone to other conferences in this, such as in the Ruby community, where big data is also a very hot topic. And the thing I've heard about processing data through tools like MapReduce is it feels hard to get started. But I don't think that it has to be. And so we're going to build a streaming Amazon Elastic MapReduce job in Ruby and run it. So again, what's our starting point? Our starting point is logs in S3. And in this case, we have them formatted roughly like this to understand why that is useful. One common pattern as you store files in S3 is not only to separate objects across buckets, but to separate across prefixes. So why is this handy? Well, one EMR mechanic that's available when you're building your jobs is to specify an S3 prefix, and it will pull all files within that prefix. So if we have date-separated logs, simply saying the input is anything in this bucket with this prefix will only include the files that we actually want to be processing, so we're not processing the same data over and over again. So to go back into it, in this example, I've generated a decent amount of logs. So we're talking a few gigabytes every day for the example scale. And I've used prefixes to separate each day's logs into a different virtual folder. And that's going to be our starting point. So from there, we're going to build a system to process those logs using Amazon Elastic MapReduce. So to start off with, what is Amazon Elastic MapReduce? So for the sake of the kind of jobs we're building, the main concepts we want to think about is that it's a cluster of machines with a master instance that does tasks such as job tracking, and worker mappers and reducers. And Hadoop will, on top of this, provide orchestration to split apart your input files to send into the mappers, sort your mapper output, and provide that into your reducers. And then once your reducers have output, put them into output files that can be ingested or used any other way you'd like. So along the same concepts, a cluster is made up of usually one master node and an indeterminate number of slave nodes, depending on the size of your workload and the type of the workload. And we'll get a bit more later into how you would select these and how you would design your cluster. So let's talk about streaming jobs. Amazon Elastic MapReduce has a built-in streaming jar. You don't need to provide it, it's available for you. And you're going to bring your own mapper, which is an executable file that can take input from standard in and write to standard out. And you're going to bring your own reducer along the same lines, and we're going to walk through that here in this presentation. Again, Hadoop does all the orchestration around this. We just focus on making sure our mapper is correct and our reducer is correct, and we can trust the system to do its job. So how's the mapper working? Again, we're taking input line by line from standard in. In the Ruby sense, the argf variable is a stand-in for this and will work for our code. Now, some of you might have a bit of a raised eyebrow, the fact that we're using Ruby to write a MapReduce job. In one sense, it's because I can make the code very concise and easy to show in a presentation. It's also a great choice for prototyping a more complicated MapReduce operation before you go and write it in lower level languages to try to squeeze every bit of performance out of them. And again, the output goes to standard out in a streaming job. So the bottom line, what we're doing is filtering values. And let's take a look at what that looks like in code. So what I have here is a working mapper code. Again, it takes line by line input from standard in, which in this case is each line of that sample log file that we showed before. We're going to split it by spaces. And if it's not a full-sized value, like if there's like just a new line, we're going to skip past that and not try to process it. And from there, we're filtering out the particular values inside the sample log that we care about. So we're going to skip the IP address. So why might we do that? Well, one important concept when you're building a data processing job is you're probably wanting to reduce the size of the log file that goes into it. Or you're trying to create more duplicate values that you can tally up with a count instead of simply storing one for one everything inside your logs. So for example, we're going to drop time of day on the floor. You might choose in your own applications to not do that or to roll up to an hourly level, a minute level, or even a weekly level. It depends on your application and what questions you're trying to answer. So what this code is doing here, and it is more heavily annotated in the open source repository. We've taken out the comments so it can help fit in this screen. But we're taking out from that string the different values we care about. And then we're turning it into pipe delimited output and then putting after a tab a 1 for the number of times we've seen that particular log entry in the mapper. The fact that we only have one tab right now is kind of important, because by default, Hadoop is going to say everything before the first tab is what I'm sorting. So if we tab delimited the entire output, it would just sort our output by IP addresses or usernames, and it's not that useful. So we want to make sure that Hadoop knows how to sort this. Another helpful thing is you can actually test this. So we have the sample log from the earlier slide, and we can run this Ruby code locally to get a good idea of how well this is going to work. So if I cat the sample log and run that mapper script, you'll see that it transforms by reducing the log file to a smaller size, pipe delimiting it, and this is something that can be passed into Hadoop sorting and later reduced. This is also very helpful for building unit tests or integration tests of your mapping and reducing code, if you can test it locally without having to build a cluster, and this allows you to do that. Next, let's talk about reducers. So again, we're getting input from our mappers that's sorted by Hadoop by the time it gets to the reducer, and that's important for how we're going to write it. Again, we're getting that mapper output line by line through standard in. And we're going to transform that output mainly by counting the duplicate keys and reducing it. And this gives us a lot of our file storage savings that we're going to realize when we move this into Amazon Redshift. And again, the same concept with the mapper, we do output to standard out. So let's take a look at the reducer, and there's a little bit more code here, but the concept is pretty simple. If you remember from the testing output we had, and we say it's sorted by Hadoop, you're going to see that there are some duplicate entries in this log. Essentially, the same, roughly the same operation happens many different times, and we're going to reduce those into a single row that's going to go into Redshift. And that's what this code is going to accomplish. So what it does is, if we see the same key multiple times in a row, we build a count, and when the key changes, we output our result. So again, we get items line by line. We're tab delimiting them now so that we can ingest them into Redshift more easily. If we have every row delimited or column delimited by the same value, we're going to have an easy time writing the ingestion code, as you'll see later. And then we simply roll up the duplicates and output to standard out, and that's all the reducer needs to do. So we can grasp this. We can understand this. Writing a mapper from standard in to standard out is not hard. Writing a reducer from standard in to standard out is not hard. When the orchestration around that is handled, now we're cooking with gas. We're almost there. So just to summarize how we built this log processing job, streaming mappers and reducers are executable scripts. It could be a shell script. It can be a Python script. It can be written in Go. You can write it in anything that you like, as long as on the Hadoop machines, you can give it an executable command to run. Hadoop manages the orchestration around the streaming. All you are bringing is a notion of where the input is, where the output is going, and how we're going to do the map and reduce operations, which you can test locally. The input comes through standard in, and the output goes to standard out. It's the golden rule every time you're writing these streaming tools. And again, it's very important to remember that you can test this locally, and this is very useful when you want to keep your development cycle tight and you're writing more complex mapper and reducer scripts. So to show you what this looks like, we remember the sample log we were looking at before. If we take this all the way to the end, we have duplicate entries. They've been reduced together. It's tab delimited, and we're down to only the fields that we care about. In other words, we're ready to put this into a database and do something a little more interesting than read a now tab delimited, still human not understandable file. But before we get there, how are we going to orchestrate these jobs? Automation is important, and this is one of the biggest lessons that I've learned in actually building a system like this. So we're going to use the AWS SDK for Ruby to automate the creation of these jobs so that we can batch and scale that work. The core concepts around a streaming step that we need to know to do this automation are our mapper and reducer source files, a notion of where our input files exist, a notion of where they're going, and what we're going to do is we're going to live code the EMR API call that we need to make this happen. So we've built our mapper, as we've seen. We've built our reducer, as we've seen. We've put them up in S3, and now we actually want to run it and see it work. So what I've got here is the beginnings of the EMR API call. The name is obviously whatever you'd want your cluster to be called. The AMI version, we're actually now also on AMI version 4. So this is not going to often change between different clusters in a system that you create. The instance groups, that's going to be a little bit more interesting. That's a bit more involved, and that's going to be one of the things that we're live coding. The EC2 key name is important because if anything is going wrong in our cluster, and this can start to happen at scale, we're going to want to be able to get on there and figure out what's going on inside of our cluster in real time. So by providing an EC2 key name, we're going to be able to do that. Finally, we have the steps. In this example, we're only going to have one step to keep it simple. We're going to process logs and give it an appropriate name. We're going to terminate the flow if the step fails because there's no more work and we don't want to have a non-working cluster operating. And again, remember how we said that the Hadoop streaming jar was built in? We can just point to a path on the instance and it'll be there, and this will be the streaming job that you need to run the code we've just written. The arguments are what's interesting, and that's the next thing we'll dive into. Finally, with EMR, you want to make sure that you're including job flow and service roles. These are defaults that are generated the first time you create an EMR job. And if your mappers and reducers only are processing line-by-line input and sending them out, this is all you need. If your mappers or reducers are, for example, calling out to different AWS services, you may need to craft your own IAM roles to do that. And any of you who are running into a situation like that also, feel free to talk to me after. It's a little more involved than what we're going to get to in this talk. But like many things, it's pretty approachable once you get down to it. So first, we're going to look at instance configuration, which is just answering the question, how many workers do we need, and how big do they have to be to handle the job that we're giving them? It's important to note that master and worker nodes are not doing the same thing, and so you might need to have different instance types appropriate to what they're doing. To dive a little bit more into that, as we remember from the earlier graph, the master node is generally doing job tracking and orchestration, which as a job gets very, very big, might be a very memory-intensive task, while your worker nodes could be doing tasks that are less memory-intensive and are more CPU or network-bound, in which case the same instance type would not be appropriate for both instance types here. And let's actually live code that and see what it looks like. So right here, the instance groups are an array, and it's going to be an array of hashes that describe the type of instances we're creating. And all of the descriptions of the arguments we're using are available in the EMR documentation and the AWS SDK for Ruby documentation, or really any SDK's documentation that you're going to use to build this kind of system. So we're going to have a master group and a worker group. Now, the on-demand parameter obviously just means we are taking on-demand instances. As you build out a system and you have an idea of how you're using it, you may choose to get your instances from reserved instances that you've purchased, or you may get your worker nodes from the spot market if it's okay if the occasional job fails. But for simplicity, we're using on-demand here. Obviously, the instance role is a enumerable value of specific different types of instance roles that are specified by Hadoop. We're going to choose to use M1 large instances. A little bit arbitrary for this, but it's just going to be a value that's going to work. And then finally, we need our worker nodes. Again, many of the same concepts. It's on demand. The core enumerable is how Hadoop describes instance workers. And more arbitrarily, we're going to choose an instance count of 5. And again, as you start to look at how your jobs are running in real life, you will start to kind of tweak that number up if you have CPU-bound jobs, or maybe if you have a job that's not using much CPU memory or networking at all, your instance is way too big, and you could have a smaller instance and perhaps more of them. Parallelism is definitely a virtue, especially as you scale. So those are the instance groups. And let's go straight to understanding the arguments that are going into the streaming step. Again, the first concept is where are we getting our source files from? So these have been uploaded to S3. So we have our mapper and reducer available, and we just need to point Hadoop to where those are. Now you might notice that we just did something cool that probably doesn't come with your garden variety Hadoop distribution. And that is that these files treated S3 like it's just part of your local file system. And that is functionality that Amazon Elastic MapReduce provides for you. And we're going to be using this very liberally to make our system as simple as possible. So next we specify where our input is coming from. So again, we described earlier the way that we've been storing our logs, and so we can simply say, this prefix is what we're going to build our job on top of. And then finally, as we've discussed, we're going to say where the files are going. Then the last things we need are just to tell Hadoop what command it needs to run the mapper, and what command it needs to run the reducer. And this is where your arbitrary executables go. So it seems like a lot when you get started, but the EMR API is not very difficult to tame. And once you've done that, you get a lot of time savings. And so now if we actually run this, we have a job flow created that's going to have everything that we've specified. It's going to know what jobs to run, where to pull input from, and where to pull output from. So for now, we're going to get rid of this because we're going to get into a little bit of a more interesting example later, but this is just to show you that the EMR API is approachable. You can write this, and once you've done that, you gain a lot of automation benefits. And let's talk a bit more about that. So really quickly, raise your hand if you've ever created an EMR job before. So quite a few of you. And how many of you did that through the console? So actually less of you than I expected. And it's the easiest way to get started with it. You click through a few menus, it guides you through what you need to do like we've just done, and you have a job up and running. Using the AWS SDK, it's very similar. We build those options as we've described and run a single API call to get it going. So what happens when you're running 100 jobs a day? Well, using the console is suddenly a little bit less appealing. You could do it, but it's going to take up a lot of your time. But with the AWS SDK for Ruby or any of our SDKs, it's still just one command. So how is that possible? It's possible through batching. So once we have batched our jobs, you get an end state in production something like this. You have different sized clusters that could be running multiple steps from 1 to dozens to hundreds. It all depends on what kind of processing you're doing. And you can run this with a single API call per cluster. And as you start to need to run dozens of clusters a day and run hundreds of steps every day, it's just a script that you can kick off with a cron every morning. So let's take a look at what batching looks like. So we've changed our log processor a little bit from what we just coded. And everything that we've done here is annotated in the GitHub repo that is going to be linked to at the end of the presentation again. But the important thing to note here is we're just separating out what separates steps from each other from what is global to the cluster. And as it turns out, describing these steps is not really that difficult. You have different names, optionally but recommended. You have different input prefixes because you're not processing the same data multiple times, and you have different output destinations. In most cases, everything else is basically the same. So once you've written this once, the amount of code you need to describe the different steps that you're going to run is not a lot, and we can get this up and running quite quickly. So what this does here is it runs a job that takes our shared instance options, which are the same as what we wrote before, the different options that describe unique steps, and is going to create a job from those. And the short version of that code is here. Again, I highly encourage you to look at the annotated repo when we're done. It's a great starting point as you start to prototype these kinds of applications. But let's run our batching example. So again, it's one quick API call, but we've made a job that's quite a bit more substantial in that process. So it's going to provision the instances that we've described, but now we have multiple steps that are each unique to the input and output sources that they're processing. And you'll also notice a little other step has snuck in here to set up debugging. This one is really important in production, and if you look in the log processing code that we wrote, we actually snuck this step in to be the first step that every cluster runs. And what having this step does for you described right here is all of the logs that are generated by your tasks, your mappers, reducers, and the orchestration code are available to you. So if a job fails, you can go dig into the logs and figure out what happened. Otherwise, your logs die with the cluster. So this will put them into an S3 bucket that you specify. And if we take a look here, you can just see that every single job flow we create has a very large amount of logs that we can go through. So this is going to take a while to run. And so we're not going to worry about this for now. But we have run this earlier, so we can show you what it looks like at the end. So it provisions the instances, it goes through each step, and then we have processed log output that is ready to go into Amazon Redshift. It's going to run the mappers and reducers using the same pattern that we saw locally. And we're ready to move on. So again, to wrap up, using the AWS SDKs and the EMR API allows us to do automation at scale. And getting started with it is simple. You can build out this prototype in less than an hour. And then you're ready to use that as a starting point as your system gets more complex and integrates more of the logic that you need to get things done. To do that, you're going to separate common configuration from job specific. You will start to build out a control plane that describes the jobs that you need. And then we're ready to ingest the data into Amazon Redshift. So again, Amazon Redshift is a scalable data warehouse. And like the log processing system we've designed, it's ready to deal with the petabyte scale. The most important thing for writing this code is hidden right at the top of that graphic, and that's that it has JDBC and ODBC adapters. In other words, it's a Postgres database for almost all client purposes that you have. And this is really handy. So ingestion is as simple as a SQL copy command. If we provide a one-to-one mapping with table columns separated by a delimiter, which is what we've done, a single command is going to load things into the database exactly the way we expect it. So in this case, we've created a table that, not coincidentally, has a one-to-one mapping with the values that were in our log system. Obviously, if the order was different, your reducer would be shuffling around the order before you print out. There's one thing that's interesting in here that also helps with performance I'd like to draw your attention to, and that is the distribution and sort keys. A little bit of the magic is in here, and it's very worth checking out the Amazon Redshift documentation to learn more about it. But it enables some common data warehouse queries to run quite quickly. What you'll notice when you look at a table like this is you're probably not running reports for all of time. You're probably running it for the last week or the last month. So by having a sort key around that, the way that Redshift runs queries will very quickly trim out much of the data that you don't need to look at, and will give you very performant queries even as your total data crosses the petabyte threshold. And again, copying is very simple. Redshift, like EMR, can alias S3 paths. We can provide custom delimiters and simply run a command to get it in. So now let's see what that looks like. So I have an EC2 instance here that has permissions to access my Redshift database. And we have a very simple piece of code that I'll actually show here. It'll be a little bit more clear. That connects to a database using the Ruby PG gem. So again, it's just Postgres. And we have the operations needed to create our table and ingest data into it in a scalable, automatable manner. So in this case, I'm going to create an interactive shell here. Oh. And I'm doing IRB wrong. I think it's a rule of live coding. You have to get at least one small thing wrong at some point while you're going. So we can create a table, and again, it's just Postgres. And following the description we have here, we can ingest data from the bucket that we've been storing process data in. And if we go back to our output, we can follow along this prefix to ingest all of this. And then finally, we're going to run this with an IAM role. An interesting thing to notice about this code is that you do need to specify your credentials for Redshift to be able to access your data from S3. And you should never hard code this. Please, if you take one thing away from this talk, don't let it be about mappers and reducers. Don't let it be about databases. Let it be never, ever, ever hard code your credentials. And so what we're going to do is we're going to take it from an IAM role on the EC2 instance. We pull the credentials from EC2 metadata and provide that to Redshift, and it will work. And it's not really cooperating with me right now, so give me 1 second. Okay, so running this ingest data process is quite quick. Even where, if you look at the output files we've generated, we have solidly over a gigabyte of output data, which is helpfully parallelized for you by EMR for the easiest loading into Redshift. Running a load query, let's go back to that load that we just did. Running that load query only takes about 1.5 minutes. So it is definitely not going to be the slowest thing in your data pipeline. So we can see running that command to copy into the table takes just about 1 minute and 6 seconds for over a gigabyte of data. And that's helpful. So again, Amazon Redshift, the interface is just like SQL. You can alias with an S3 source just like you do with EMR. It's ready to load from the EMR output structure. And now we can start to talk about how we generate reports once it's in Redshift. Now again, this is kind of cool because when I was writing this talk, I was using the tools that were available to me. And now we have a new one, which is the business intelligence service that was talked about at the keynote, I believe, 2 days ago. This one. There's so many, I'm losing track very quickly of how many new services that we're launching. But this is actually going to be really helpful. And again, any other tool that you have that can build reports off of Postgres databases is ready to go with this system. So you can go from a simple count query of how many users you have. You can have date-ranged queries about how many requests you're getting to your website. Or maybe you didn't anticipate that your CIO really cares about this ad campaign he's been running, and he wants to know how much activity is coming from your newest registered users. But all of that can be done through Redshift, through a SQL query database, and it operates at the scale that you need. And again, going back to the beginning, this supports planned reports. So you're saying, how many requests am I getting every day? And you're emailing it to your CTO every morning. You can do that. It supports ad hoc queries through any Postgres adapter that you can bring. So we have programmatic reporting with SQL, query logic that's not Redshift specific. You don't have to learn any new Redshift query language to get things done. This was probably the fastest part of building a system like this for myself. I knew SQL, I'd never used a data warehouse before, but writing report queries is easy. I wrote the queries the way I would do it for any other SQL database, and they just work. Columnar storage optimizes for common data warehouse queries. Breaking apart your queries by end dates will give you a huge performance benefit. You can use S3 to store reports, which is very handy. You can have the output from your reports go into S3, where it's available to almost any other tool that you have. And you can take advantage of some interesting Postgres SQL features like window functions and common table expressions. So let's take a quick look at some of that. So in the repo that we've linked, I built a very simple reporting tool that, again, just connects to it like any other Postgres database and runs a few example interesting queries on the data that we've processed to see what we can learn from it. And so let's take a look at that. Okay, and that part seems to be missing from my instance, incidentally. But the idea is, if you look at the queries that we've provided here, you can get very quick turnaround on how many users you have, how many requests you have each day, or what were your top product pages if you have an e-commerce store, for example. And you can build these queries quite easily. You can turn them into CSVs and send out an Excel sheet every morning to anyone technical or non-technical that you need to communicate this with. So let's dig into some of the finer points of this as we start to go into production. So this is a nice toy that we've built. It operates on a few gigabytes of logs. You might have more than this and you think, okay, this is great, I can get it to work. But can this actually scale? Can this scale to the needs that I have? So before I get into this story, I always feel like reminding mainly myself of exactly how big a petabyte is. A petabyte is a lot of data, 1,000 terabytes. or 1 quadrillion bytes, and I actually had to look that number up because I didn't know what it was. I just knew it had a lot of zeros. Well, one day I had a problem, or I had 5 quadrillion problems. And that's a large amount of the data that we had was wrong. We had an incomplete input source. The system was running fine, but if you have bad garbage data in, garbage data out. And I had to replace 5 petabytes of data. And like any time that you have an inaccuracy in something that people read, they needed it last week. So I needed to fill this up really, really fast. So what do you do when you live in a world with AWS? Well, you spin up 1,200 machines, you churn through that 5 petabytes in about 36 hours, and the new data is there and everybody is happy. And once I was done, I grabbed all those 1,200 machines and I threw them in a dumpster out back and refused to pay for any more of their time. It seems crazy, but that's what you can do. If you have a giant amount of burst capacity above what you use every day, you can get that done. You can use on-demand instances, you can use spot instances, you go through your load, and then you drop it all on the floor and you don't pay for it again. And I want you to close your eyes for a second and imagine 5 years ago or 10 years ago what is happening to you if you have this problem to solve. You can open your eyes. I don't want to give you nightmares. I don't want to have that on my conscience. So what did we learn from doing this? It wasn't necessarily easy. Well, one, as I've alluded to a few times, master instance selection matters. I was lazy and I was using the same instance type for my masters and workers. And as soon as I tried to spin this up the first time, it was way too much data and the master just completely failed. The job tracker couldn't handle how much data was coming in. The workers were fine, but the job would never complete. And we had to use a different instance type that had a lot more memory to be able to support the size of our load. So you want to pay attention to what kind of master instances are you selecting for the kind of jobs you're running. The memory on your workers matters. How many mappers do you need to run for how much of the workload is based on mapping? How many reducers do you need to run? How much memory do they need to get their job done? As little as needed so you can parallelize as much as possible, but enough so that mappers aren't persistently failing and your job never completes. And the final thing we learned is that elasticity is awesome. The fact that we could spin this up so quickly and spin it down just as quickly enabled us to solve a really scary problem in a couple of days and not have to deal with the persistent budget of building out a new data center just to solve a one-time problem. So the last thing I'd like to talk about is a few more lessons you're going to learn as you bring this into production. And as I've hinted to again, repeated manual tasks are evil. They start out innocently enough, but then you're spending all of your time looking through output, making sure everything's there, looking through your database, making sure things loaded the way as they expected. Anything that you can automate, please automate it. Don't do it for me, do it for yourself. Having multiple sources of truth is important. We didn't get to 5 petabytes of bad data overnight. We got there because we weren't checking with other potential data sources to see, are we actually loading everything that we need? So if you have multiple sources of truth, try to check against them. See if your numbers are different. Sometimes they're wrong, sometimes you're wrong. But if you have these multiple sources of truth, you're not going to be wrong for nearly as long. Understand the storage ramifications of your table design. If you want to keep track of IP addresses, if that's important to you, you're going to need to store potentially a lot more data if users are changing IP addresses a lot. So are IP addresses important? Can you drop them on the floor? Do you need to have down to the second granularity about what people are doing with your system? You can do that. Redshift can handle it. EMR can handle it. But you're going to be storing a lot more data. So if you want to keep your ops people happy, Be judicious about what data you're saving. Automate your validation. Again, notice that we've been storing our data in S3. It's as simple as a list objects query in S3 with the prefix I expect to have output to say, did my job actually finish? Or if it did finish, did it actually produce what it said it was going to produce? You can automate these things and just kick off a new job if you had a job failure. They happen from time to time. And so for validation, again, it's the same concept of checking through the examples, making sure that, if I expected 10.8 to have data right now, run that query and create a new job using the control plane we described without you ever seeing it. Periodically in the system I maintain, we do hundreds of load jobs every day. Almost all of them succeed, 1 or 2 a day don't. A couple instances die, the job doesn't complete successfully. I never really notice because the next morning a validation job runs, and statistically they almost never fail twice. And when they do, you just run validation again. So I've taken away that manual work from my life, and I'm a lot happier for it. And remember, you don't have to do this all yourself. This is not a show and tell. This is a prototype. This is a guidepost that says if you don't know how to do MapReduce going in, you can start with this and you can build a real system following these patterns. But there are a lot of related services that help you. Not only the new BI service, but AWS Data Pipeline can help you do this orchestration. And now you'll understand what it's doing for you behind the scenes. Amazon Machine Learning can give you a lot of really helpful insights on that data you've spent all that work putting into Redshift. Kinesis can be another source of input. Maybe you're streaming data in real time into Redshift, and Kinesis can do that, and now you know the concepts behind it. You can send out those reports that you've put into S3 using Amazon Simple Email Service or Amazon Simple Notification Service to even build an API around it. Make API calls every time a report is done if you need to. And also, one thing I've noticed as I walk around the huge booth area is there are numerous AWS partners that are more than happy to help you answer some of your data problems. So check out the AWS Marketplace. Anything that's going to work on top of Postgres is going to work. So to wrap up, we know how to build an Amazon Elastic MapReduce job. We know how to automate this cluster creation using the AWS SDK. We can format those results and ingest them automatically into Amazon Redshift. We can create useful reports using any tool that can be built on top of Postgres. And we can start to think about how are we going to scale this system and how are we going to run it in production. And that's really why we're here, and that's what matters. So there are resources, and again, I will be tweeting these out, and the slides should be available, and the talk will be again available on YouTube if you'd like to review. Check out the sample code, play around with it. There's a lot of really helpful insights in the Elastic MapReduce documentation and the Redshift documentation. And everything you need to build these API calls and more is in the documentation for the AWS SDKs. You can find me on Twitter. I'd love to hear about what you're building and what questions you still have. So thank you very much for your time.